In this video, we are going to learn series circuits containing R, L, and C, resistor, capacitor, and an inductor, all in series within the circuit. If you have a circuit like this, how do we find the impedance of the entire circuit, as well as the phase difference between the current and the voltage, since we are dealing with an AC voltage? In our previous lessons, we've learned series circuits containing R and L, then containing R and C. So it is time for us to learn the combination of all the three elements. So we know that from Kirchhoff's voltage law, our total voltage V is equal to the voltage drop VR plus the voltage drop VL plus the voltage drop VC. Alright. So at this point, let's draw our phasor diagram and see how we can find our total impedance. Since we have all these three elements, this resistor here is a direct component so that the voltage and the current are in the same phase. For that reason, it always takes the direction of the current when we are drawing our phasor diagram. So this is our current, our VR will be in the same phase. Our XL and our XC are rather having the voltage and the current not being in the same phase. For that reason, our XL always take the positive Y direction, whilst the XC takes the negative Y direction. This is because current in an XCR circuit leads the voltage, whilst that of the XL it rather lacks the voltage. So the capacitance, that is inductive capacitance, or the voltage across the capacitor, comes down. Here becomes our VC and here becomes our VL. So we can put the voltage here or anywhere here. So this is our voltage V, which is the phase difference here. And in this manner, it is leading towards our I because it is in the VL direction. Once we want to use this section, this place becomes what? VL minus VC. So it is three elements all acting alone. So the effects, you see, this one is pulling forward, this is pulling back. So the combined effect of these two affects the orientation of the voltage and the current. Depending on the strength of the inductance, the direction will move in the opposite direction. And if the VC is stronger, it will rather what? So if the VL is stronger, meaning that you have this direction, if the VC is stronger, it will shift to this side and our voltage will then come to this side. So always when the three are combined, the difference between the VL and the VC is considered as the effective reactance. We call it reactance. So we have reactance and we have resistance. In an AC, reactance is introduced by our VL, that is the inductor, as well as the capacitor. For that reason, the effective reactance will act here and our resistance is in direction with the current I. With this little explanation, we know that by vectors, this place is the same as VL minus VC. Our total voltage V will then be equal to V squared will be equal to VR squared plus VL minus VC all squared. Right. So at this point, I'm going to have my total voltage to be total current times the total impedance squared equals total current times the total resistance squared for the VR plus my IXL squared. So sorry, the IXL minus IXC all squared in this manner. Once I have this, I can factorize my I squared out here. So that I'll divide through by I, then I'll have Z squared equals R squared plus XL minus XC all squared. My Z is equal to the square root of R squared plus XL minus XC all squared. And this gives us the total impedance in an RLC circuit. Now, once we have our total impedance, so if you have a circuit having a resistor, a capacitance, and also the inductance, we simply square the resistor plus the difference between the two reactants squared. At this point, let's find the phase angle between the voltage and the current in this manner. So you can see that since we are having the effective reactance which may be in the direction of the VL or the VC, we will have two situations of theta. So now let's see. Tan theta is simply equal to, sorry, let me make it theta itself is equal to tan inverse of our VL minus VC over what? VR, right? Which is also going to give me tan inverse of XL minus XC over R. Now, if my XL is greater than my XC, then meaning that my theta here will be positive. Theta will be positive, and it means that the current will lag the voltage supply. So meaning that the inductance here is stronger, and hence current will rather lag the voltage. So current will lag voltage. The second scenario is when XL is rather greater than or less than, let me make it XL less than XC. When XL is less than XC, you get a negative angle. So the angle will be negative. And what does that mean? This means that the current is rather hot, leading the voltage. And when a current is leading the voltage, it means that the reactance is what? Capacitive in nature. Thank you for being with me in this class. See you in my next class. We'll be solving more problems in RLC circuits.